Good evening, Carolians. This is an update on the James Webb Space Telescope, sitting there a million miles above midnight. I'll try to keep this relatively brief. As we all know, England are playing. So, back in December 2021, Christmas, that's why there's holly in the top left and bottom right corner. This is a Christmas talk, despite the fact that it's currently July. Back then, it was launched to L2, and it's sitting there a million miles above midnight, and it's been doing its stuff for over 2 years now. What's it supposedly doing? Well, it's looking at lots of things, including looking back in time. If we think about this timescale from the Big Bang to now and the number of billion years since then we can think about how far back in time it's looking by thinking about how much the light has been stretched before it reaches the James Webb. If it hasn't been stretched at all, it's coming from somewhere local. If it's stretched to twice its wavelength, that means it's coming from a period about 5 billion years after the Big Bang. And we can get back to about a Z of 4 without even using a telescope. But the Hubble Space Telescope has taken us beyond a Z of 4 because we're interested in this time period here. The first billion years or so is the time period where we think the first stars and first galaxies came into being. If we expand that out so we can see it a little more clearly and expand the first 500 or 600 million years, we hope the Hubble Space Telescope will take us back to about a redshift of 10. That takes us back to about 500 million years after the Big Bang. Once the James Webb has been in operation for a while, we hope to be able to see even earlier stars, perhaps back to as early as 200 million years or less. That's the holy grail, if you like, to find the first stars which we think would have been born in this sort of period. So we know that there were some fantastic things coming out of the James Webb 6 months after it was launched, but this is a 2-year update. So I'm going to look at what the main results were in 2023. So I'm just going to pick a few highlights. It's not supposed to be comprehensive. So back in January 2023, it released these images of a solar system seen edge on. We're looking at the dust in a solar system. For those of you who've seen the dust within our own solar system, the dust is mainly confined to the ecliptic plane, and that produces the so-called zodiacal light, this faint light that can be seen sometimes after sunset or before sunrise. And so here we're effectively seeing zodiacal light from another solar system, which is pretty incredible, given that in some cases it's rather difficult to see even in our own solar system. In February 2023, James Webb announced that it had seen a 150-meter diameter asteroid. That's this artist's impression, doesn't really indicate quite how amazing that feat is, because the asteroid wasn't close to Earth at the time. This 100-meter class asteroid was actually still inside the asteroid belt, and James Webb just happened to pick it up by accident because it was looking for something else. So that gives us an idea of the sensitivity of the James Webb. With such a large mirror, it can pick up small objects at great distances. Unfortunately, it's not looking for asteroids that are going to pummel the Earth, so even though it has that sensitivity, it's not going to be used in that particular mode. In March, we were treated to this image of a Wolf-Rayet star, Wolf-Rayet 124. It's believed that these types of stars are very unstable and might be the precursor to a supernova. This one, from its appearance, looks like, from the knotty appearance of the nebula surrounding it, it's been losing mass for quite some time. Maybe for thousands of years, it's been sloughing off its outer atmosphere. It's thought that this particular star is about 30 solar masses, and it's estimated that it's already lost about 10 solar masses into the nebula. So maybe this particular candidate is ripe for being a supernova in the not too distant future. In May of 2023, we saw this image of Fomalhaut, the brightest star in the southern fish. And it's tempting to look at this particular dusty solar system that we're seeing here. We're not necessarily seeing individual planets, but we are seeing definite rings that presumably have been formed due to the nature of planets that are circulating in this solar system. And although it's not strictly accurate in terms of scale, we can perhaps look at this and think, is this an analogue of the inner ring being somewhat similar to our asteroid belt, and perhaps the outer ring similar to our Kuiper belt? Again, the distances don't quite work out, but it's tempting to think that we are looking at a solar system in the process of formation along the same lines as our own solar system. In June, they released this picture of Pandora's cluster. It's been imaged before by the Hubble Space Telescope, but Pandora's cluster here, imaged in a mosaic, is incredible for the amount of detail that the James Webb has been able to pick up. Thanks to its larger mirror, the resolution, remember, will be very similar to the resolution of the Hubble Space Telescope, but with a larger mirror, it will be more sensitive to fainter objects. And it's been estimated that in this mosaic of images, there are something like 50,000 sources, most of which will be distant galaxies. So plenty of data to keep scientists happy for many years into the future. In July 2023, that was the first anniversary of its scientific data production, the first scientific releases, and so for the first anniversary picture they took this of the Rho-Ophiuchi cloud complex, or at least a very small part of it, if we remember that the James Webb has a very long focal length, more than 100 meters or so, and hence it's only looking at a tiny patch of sky. But this particular region is one of the closest star-forming regions to us. The star in the bottom here seems to be excavating a cave in this nebula around it. This is thought to be a star-forming region very similar to how our sun might have started its life. But in addition to that, we see these rather amazing stellar outflows, these jets that are coming from a region where presumably there are some stars buried in this rather dusty environment here, through which even the James Webb can't penetrate. And these jets indicate the formation of stars producing large energetic outflows, and we'll see more of those in just a moment. In August, they released this image of the supernova in the Magellanic Cloud 1987A, and what we're seeing here is material that's been expelled from the supernova probably a long time before it actually went supernova. Perhaps thousands of years earlier it started producing material which ended up getting expelled into the interstellar medium. And then when the star did go supernova, it produced a shock wave, and the shock wave has now caught up with that material and produced this sort of string of pearls effect as the shock wave is now ploughing in to the interstellar medium, which has been enriched by all the material that's been ejected from the star before it went supernova. So it'll be rather important to continue watching this in years to come to see how this structure evolves. Astronomy picture of the day in September was again protostar jets. In this case, there's some sort of star embedded in this very dusty region, which again the James Webb can't quite penetrate, but it's clear that we've got these jets forming, and these jets are producing shock waves as the jets slam into the interstellar medium. And this particular system is quite interesting because although we can't quite see it in this image, close inspection of these jets indicates that they are braided or twisted. And it's thought that these jets are twisted because what's going on in this invisible area right in the middle is perhaps the birth of a binary star. And that's what's twisting these jets into these structures. So perhaps we're witnessing the birth of a binary star, which hasn't been seen before. In October 2023, there was an announcement of one of the brightest gamma-ray bursts ever seen, a so-called kilonova. It might not look very spectacular here, just a tiny red dot, but this particular kilonova has been associated with the merger of two neutron stars. The neutron stars were, it's thought, born in this particular galaxy, but when the two neutron stars were made in a supernova explosion, or two supernova explosions, then they were kicked out of this galaxy and have been travelling over this vast distance and eventually merged together to produce this kilonova when they were in the position as indicated on the left-hand side. It's not necessarily the gamma-ray burst that was particularly interesting for the James Webb. It was the fact that when it took spectra of this object, it found the telltale signs of an element called tellurium. This is an element which is about twice as heavy as iron. And therefore, this is an indication that very heavy elements beyond iron are not only made in supernova, they are also made, perhaps in significant quantities, in the merger of neutron stars. This was thought to be the case, but now we have proof that that is actually the case. And it might actually be that the merger of neutron stars actually produces more of these heavy elements, silver, gold, tellurium, lead, etc., compared to supernova explosions themselves. In October, we were treated to this view of the Crab Nebula from the James Webb Space Telescope. It shows a similar structure that we've seen before with the Hubble Space Telescope, but now we have this sort of milky background with these rather odd striations. What we're seeing here is so-called synchrotron radiation. It's radiation from charged particles in strong magnetic fields. And if we look at the lines here, we can start to trace out the magnetic field lines that are within the Crab Nebula. And indeed, we see this sort of spiraling structure indicating that we have a very strong source of magnetic fields right in the heart of the Crab Nebula, the neutron star, the pulsar that's generating this entire structure. If we compare the James Webb picture taken recently with the Hubble picture taken about 20 years ago, if I flick backwards and forwards between them, there's the original Hubble picture from 20 years ago, there's James Webb, Hubble, James Webb. Perhaps you can see there's a change in size. If you fixate on one particular part of the structure of the nebula, for instance, and just look at that, you can see that there's a definite change in size. Remember, these images are 20 years apart, and this nebula was seen to be generated in a supernova that was seen in 1054, about 1,000 years ago. So 20 years as a fraction of 1,000 years is a few percent. And that's why, that's why the nebula seems to have grown by a couple of percent in those 20 years, because it was originally formed 1,000 years ago, and so it grows a few percent every decade. So we're learning more about what produced the supernova, because James Webb can take spectroscopic information about the iron and the nickel and about the formation of the supernova, as well as how it's interacting with the interstellar medium. Towards the end of the year, astronomy picture of the day in November last year was this picture indicating the earliest known supermassive black hole. This is again Pandora's cluster, but it's not the foreground cluster that we're interested in, which is a few billion light years away. It's the fact that this large cluster, this large supercluster, has actually lensed and hence imaged much more distant galaxies. If we zoom into this small square at the center, it's not this bright object we're interested in, not this one here, it's this very faint object right next to it, which hardly shows up at all in the James Webb image, but is quite bright when we look at it in X-rays using the Chandra Space Telescope. So we have an object here which is very bright in X-rays, but rather faint in infrared light. So this would indicate that the origin must be a supermassive black hole. That's the only way of explaining so many X-rays from an otherwise rather faint and distant galaxy. So James Webb has been able to take the spectrum of this galaxy and determined that its redshift is 10. So this is a very early part of the universe. This is perhaps only 500 million years after the Big Bang, the earliest known supermassive black hole. So the problem for the theorists now is to explain how you can get large supermassive black holes only 500 million years after the birth of the universe. Some people think that you can only get supermassive black holes by accumulating black holes over periods of many billions of years, but here there is evidence that it only takes hundreds of millions of years before you have really large black holes. How can they get so big so quickly? That's still one of the great enigmas of looking back into the early universe. So that's 2023, and that's really what I wanted to say about JWST+2. But given that we are now 2.5 years into the James Webb Space Telescope, perhaps I ought to do a very quick update of the last few months. Back in January, the James Webb Space Telescope imaged some much closer galaxies than these faint red blobs that we've seen in the past few images. Perhaps they've been forgotten because there's a tendency to think about planet formation and star formation and not think, and also the more distant galaxies, but not think about some of our nearest neighbours. But by taking images like these of various spiral galaxies that are close enough to us to see an enormous amount of detail at various wavelengths, complementing data that we have from the Hubble Space Telescope, we've been able to get a much better idea of how stars are born and how they live and how galaxies evolve within spiral galaxies. In June 2024, we're now talking about literally only a few weeks ago, this image was released of, again, protostellar outflows. This is a very rich image in which there's lots of stars being born, and perhaps you notice some of these linear features, these jets of materials that are being thrown out of very early star formation. There's a tendency in this image for these various jets to be all in the same direction. Now, it was thought very likely that if lots of stars are born out of a large cloud and that cloud is very slowly rotating, then you might expect the stars that are born to end up spinning in the same direction, and hence the protostellar outflows, these jets of material that are spat out when stars start to form, it is expected that they might be lined up. But now we have the first evidence that yes, when we see stars that are born out of the same cloud, there is a tendency for those stars to spin in the same direction. So that was hypothesized some time ago. Now we have evidence that that is indeed the case. The JADES, the JWST so-called Advanced Deep Extragalactic Survey, a bit of a mouthful, has been looking at lots of deep fields to look at thousands upon thousands of galaxies. And in the process, it's actually discovered a significant number of supernovae. In this field alone, there are, I don't know, maybe 100 supernovae that have been identified. Far more at this distance than have ever been seen before. And this is important because if we look at these supernovae, we tend to think of them as standard candles. That's one of the ways we determine how fast the universe is expanding, is by looking at redshift for very distant objects. But we're assuming that all of these objects have the same brightness. So by seeing lots of supernovae at extreme distances, the James Webb is being able to tell with images like this whether or not these supernovae do have the same intrinsic brightness at all sorts of different redshifts. Because ultimately, if the supernova don't have the same intrinsic brightness as a function of redshift, in other words, if the intrinsic brightness has changed with time, then we can't use these as standard candles, and attempting to do so to measure the Hubble constant will give us errors. So it is important to know whether or not supernovae are or are not standard candles. And I'd like to finish with this image from Astronomy Picture of the Day, 24th of June, so literally just a couple of weeks ago. There was this image again taken from the JADE survey, and now we're zooming into a tiny galaxy here as indicated. It's not the entire blob shown in this inset, it's only this end, the red end, because this is actually thought to be two objects which happen to be line of sight close to each other. But the red object, its redshift has been determined from spectroscopy, and it's found to be a redshift of 14, which is the most distant galaxy yet found. And if we go back to our original diagram saying that we hope the James Webb pushes back the distance to the earliest stars and earliest galaxies possible, we now realise that we have pushed it all the way back to Z equals 14, 300 million years after the Big Bang. We've pushed beyond the limit of how far Hubble could go, and the James Webb is now pushing that limit still further. It is thought that that shouldn't be the absolute limit for the capabilities of the James Webb. Perhaps it can get down to within 200 million years after the Big Bang. Will we find that there were no stars and galaxies when we get that far, or will we still find objects that were born very early after the Big Bang, which will keep the theorists scratching their heads for a long time yet? So that is my whistle-stop tour of the latest results from the James Webb plus 2.5 years. Thank you for listening.